Hey, hello guys, this is Sanjay here. So we'll continue with the Aldol reactions. So many were uh, asking me about where is the Aldol condensation reaction. See, it's a set of reactions which follows similar mechanism. So Aldol reaction will come up in the third or fourth video, I guess. So until then, you have to study all the basic reactions which similar to that of the Aldol condensation reaction. And also the first video, if you did not watch, go and watch please. So in the first video, we saw about the tautomerization, which is only of the keto-enol form. Why I have taken only that is because only that forms, that mechanism is similar to the alpha reactions. Okay, so there are many other tautomerism also. We'll take up later. So now we'll see about the alpha halogenation reactions. So basically, now we come to see the alpha halogenation reaction. Alpha halogenation reaction. Okay, in the part one we saw about the substitution, not basic substitution, but that we will see today. We saw the attack taking place at the alpha carbon, right? So similarly here also the same things happen, but a halogen will get substituted at the alpha position of the carbonyl compound. We will see, take again the same example, CH3 C double bond O CH3 first. So we in the presence of some uh, base and some halogen X2 where X is equal to Cl Br I. Generally, we will not take fluorine because fluorine, because of its small size, uh, the reaction explodes basically. So we don't consider fluorine in any of the reactions. Some special reactions do exist for the preparation of alkyl fluorides and involving a fluoride ion, um, namely Swartz reaction and so on. But here we would take only chlorine, bromine, and iodine. So what it will give the product, I'll write here. So it will give CX3 C number modulo. Okay. So we'll see how this take place. First we will see the so similar thing happens here also. First I'll write like this H3C because carbon is bonded to carbon, right? OH minus ion. So be careful. As the molecular symmetry, the attack can take place here or here. So it will be CH3, C double bond CH2 minus plus H2 is the first step happening. So now comes the important part. See, this CH3 C double bond CH2 minus is actually a resonance stabilized ion, right? Resonance part goes like this. This also we have seen. This is where actually the enolization takes place. So this is basically the enolate ion. Now, as I said, um, negative charge is present on the presence of negative charge on oxygen and carbon. Do you think which is more stable? Oxygen, right? So because oxygen is more electronegative, so basically this resonance structure is more stable than this one. So the reaction proceeds with this resonance structure, okay? But an irony happens here. I'll say what. So basically this undergoes further step. Now now comes the catchy part. Essentially we add x, right? This is a halogen molecule. So that attack can directly we consider this molecule for attack and not this molecule. Okay, that's clear, right? So the attack can happen from this negative charge like this, and this X can leave. So CH3 COX double bond CH2, and now the tautomerization time can takes place. You know how to write the tautomer, the keto form of this, CH3 C double bond O CH2 X. So just fix this, or it can take place over here also. CH3 CO minus 2. This can come here. This can go here, and this can attack here. Do you realize what is happening? I'll write this basically. This is actually CH3 C double bond O CH2 minus the same compound which we got over here. This negative charge attacks this halogen, and this leaves so as to get CH3 C double bond O. Now, do you realize we get the same product here and here, but which of these step it follows? You have to think from the basic. Okay, if you see carbon with a negative charge is actually a stronger nucleophile than the oxygen with a negative charge, because the electronegativity of carbon is lesser than oxygen. So the shared pair of electrons is more attracted by the oxygen, so that it will not give the negative charge of electrons for the attack, which is basically the behavior of a nucleophile. The carbon being less electronegative than oxygen, it can easily give out the shared pair of electrons and act as a good nucleophile. This you should have read in basic general organic chemistry, which we'll try to cover up later. So this actually happens. So the possibility of attack of this molecule, negative charge forms out here, here, and this goes. The INE, what I said is actually the molecule which is formed over here is the same thing you see here. Actually, if we want to write the product directly, you could have write directly this molecule and attack the halogen molecule and make the product like this. But we have to see the depth of the reaction. So actually, most resonance stabilized structure is this one, oxygen with negative charge. But the reaction proceeds like this, and then it attacks the halogen like this. So this is the compound form. Now comes the catchy part. CH3 C double bond O CH2X. Do you realize we have two more hydrogens for the same attack? So again OH minus will come. Again it will capture the hydrogen. Again it will come CH minus X. Again. I here whatever I said, right? It actually goes like this, like this. Okay, I'll write and show you, because you have to practice this, then only it will get registered in your mind. CHX. This is in resonance. So now this CH3 is CO minus double bond CHX undergoes this halogen attack. Similarly, this hydrogen is also abstracted. Similarly, this 3 hydrogen can also be abstracted. So we get the product finally as CX3, C double bond of CX3. Now understood how it is taking place. First, the alpha hydrogen gets attacked by the base and gets removed as water. Then the inolate ion so formed arranges itself. It is actually resonance stabilized, and the resonating hybrids exist like this. This is resonating hybrids, and finally the more contributing structure is this one, as this is the more resonating structure. Now this undergoes attack like in this pathway and not in this pathway, because This I'll write down here, written here. This path is favored because carbon, this is C means carbon. Carbon with a negative charge is a weaker nucleophile, this path. And this path is not favored because oxygen cannot act as a good nucleophile than carbon. And hence, this attack goes like this. This attack, this negative charge polarizes over here, and this goes and attacks the halogen. This removes one halogen as X plus, and finally forms this one. Similarly, all the hydrogens get abstracted so that you form the final molecule like this. One more important thing I would like to say here is, with the incoming of each x in the whole molecule, that is, first we take this acetone and get this one, right? This is the first product, and we further take an attack over OH minus and X2 to get CHX2, and finally the reaction goes on to give this product. Okay, so with so here six halogen atoms gets added, right? So with each incoming of each halogen, when it enters the molecule, that is, when it gets substituted, it actually, the reaction gets more and more favored. I'll say why. Because first CH3 C double bond to CH3. Now an X attaches over here, and this is simple. Leave it. Why this reaction is favored? Because of the resonance stabilization of the negative charge over here. Now, with that, uh, uh, one more effect is uh, taking place in this molecule when it undergoes an attack of OH minus. OH minus attacks this hydrogen, it leaves and forms this, right, CH minus X. This negative charge is stabilized by resonance as well as the negative inductive effect of the halogen molecule. Understand? Inductive effect means, read in general organic chemistry. Inductive effect means a pulling of electrons towards itself, or donating electrons. So this halogen shows higher inductive effect so as to stabilize this ion. So this reaction is more favored. Now similarly, when this molecule is formed, the next process is what? Remove this hydrogen and put a negative charge here. This negative charge is also stabilized by the resonance of the C double bond group, and also by two halogen molecules, which is more than this one. So here only one halogen atom is responsible for the inductive effect. Here two halogen atoms are responsible for the inductive effect. So this is the catchy point you have to take down here. So this is the reason why polysubstituted product. Polysubstituted means, you understand, you take CH3 C double bond of CH3, and you result in CX3 C double bond of CX3. So this is about, means all the hydrogen of this atom gets substituted here, right? This is the basic idea of alpha halogenation. This almost is the mechanism for haloform reaction too, which I will say next. Similarly, we will see now the acid promoter mechanism also, which is pretty simple. So this is CH3 C1 CH3. We'll take first H plus. So lone pair of oxygen attacks here. So it will like CH3 C double bond OH plus CH3. Now this X is basically, you see the, so here X will come. So this X, I'll write like this, CH3 CH2H. I'll say why. This X come, abstracts this proton, this bond shifts like this. This will result in the formation of enolate ion. Sorry, enol. Do you understand what is happening over here? This arrow, whatever. Slide number 1. Do you see what is happening over here? It's actually, this double bond polarizes towards itself because oxygen is electronegative. The positive charge on it is not at all acceptable. So it pulls the electrons shared between C double bond O. So as to get rid of the positive charge. So charge is like a headache. So this will come over here, and imagine like here positive charge is formed. Similarly, H plus leaves. because the halogen, actually this is B minus plus. This x2 breaks as x minus x plus. The x minus abstracts this proton as H plus, right? So this goes as H plus. So you will get a form of negative charge over here. So this positive and negative forms a double bond here. This simple idea. So plus Hx, if you want to write, you can write. And also X plus, this is not needed actually. So this is the formation of enol, right? Acid promoter mechanism always proceeds through enol formation. This again goes like this. This lone pair comes over here, and this forms. This is one more molecule of X come here. So it goes like this. Number 1, arrow number 2, arrow number 3, arrow number 4. So this comes like CH3 C double bond OH plus and CH2X. Okay, essentially H plus leaves like this and forms the same product which we have formed here. Where is that here? So this is not necessary that always base and acid catalyst forms the same product, but mostly it forms the same. So this is the product through acid catalyst mechanism. Here also some catch is there. Here also all the hydrogen can be substituted by the halogen, right? But that will not happen over here. I'll say why. Suppose this again goes for the further reaction, CH2X, right? This goes for the further reaction. What will happen? H plus will come, right? So this abstracts the H plus, CH3 C double bond OH plus CH2X. What happened over here? Again, the X2 molecule came and attack this one, right? I'll write CH2 as H like this, CH2. So it came and attacked this, came like this, it went like this, CH3 C double bond O, sorry, not double bond O, single bond O, H double bond CH X. Now this is a nucleophilic center which will further goes for the attack with the X2 molecule, right? This should get this lone pair should come like this, and this should polarize over here, and this negative charge should come and attack over here, which will not happen actually because this halogen, the same inductive effect applies over here also. This halogen having inductive effect, nucleophilic center, right? This is a alkene is a nucleophilic center. So this cannot polarize over here because the negative charge, the negative effect of the nucleophilic center over here is reduced by the halogen. So both in the base catalyst mechanism and acid catalyst mechanism, the thing is that inductive effect of the halogen, which comes through the substitution, favors for the more polysubstituted product in the base catalyst mechanism, but defavors the polysubstituted product in the acid catalyst mechanism. So here only monosubstituted product is formed. This is the very important point in this reaction. Monosubstituted product forms. So in the presence of inductive effects, a group like halogen, it can happen, but this substitution also can take place over D2O, which is deuterium oxide, in presence of H plus or OH minus. Similarly, it takes place. D2O means DOD, right? So it acts like X bond X. Similarly, reaction takes place, but in case of substitution of deuterium, both acid catalyst and base catalyst forms polysubstituted product only. But in the case of halogenation, base catalyst forms polysubstituted product, and acid catalyst forms monosubstituted product. This is the catchy thing over here. So the next reaction we will see is the haloform reaction, which is also a most important reaction. Actually, the haloform. Do you know what is haloform? This is actually this one, CHX3. Okay, this is known as haloform. So where X is equal to chlorine, bromine, iodine. So CHCl3 is chloroform, which is most poisonous in the way that you can be unconscious when you smell it. CHBr3 This is bromoform. CHI3 is iodoform. So these are the haloforms we study here. So basically, these haloforms can be prepared using a free radical halogenation. I'll tell in short. When you take alkane, this is methane, in the presence of H nu, and when you add Cl2 to it, you will get CH3Cl. So one more Cl2 you have to add because of H nu, you will get CH2Cl2, and one more Cl2 H nu you have to add to get CHCl3. This is form. Basically, this is a free radical substitution of halogens to alkanes, but this methyl chloride and dichloromethane and this chloroform, and when you further go, you will get this one. You get carbon tetrachloride. So all these will be in present in mixtures. So it is uh, it is kind of difficult to separate this mixture, but still we can prepare chloroform using this. So I'll tell you how the reaction takes place, but there are for the haloform reaction to take place, there are some structural arrangement which I'll tell you later. First, I'll tell you using this acetone only. You always take acetone as example. So this will undergo, as we have seen in the alpha halogenation, it will undergo, it will take basic medium only. So OH minus, it will undergo this one, CH3, C double bond O, CH2 minus plus H2O. Now this CH3, C double bond O, CH2 minus will undergo this one. This will be under resonance. So this is more stable, more resonating structure, and as carbon is the nucleophile, carbon is the strong nucleophile. We have seen right just now in alpha halogenation reaction. So it will come like this, and we'll take X, it will go like this. So CH3, C double bond, no, it's 2X, and the reaction proceeds further to form CH3, C double bond, no, CX3. Now up to this, the mechanism is same as alpha halogenation. That's why I said the mechanism is so similar. Now I'll say what happens. Now one more molecule of basic medium, right? So OH minus will come. So now what happens is the most important step. Now this OH minus ion attacks this carbon. You can ask, this hydrogen can also be changed to CX3, but the haloform reaction actually is trying to form a carboxylate ion. So we actually, when we do mechanisms, we get the product and depict some way which does not deny the rules of organic chemistry, and then predict addition mechanism for this. So the OH minus ion now attacks this, and this goes. This carbon here is sp2 hybridized, right? Hybridization. So now what happens? CH3, CO minus, CX3, OH. This carbon is sp3 hybridized. sp2 hybridized has an angle of 120 degrees, right? Somewhere around 120 degrees, right? But sp3 hybridized carbon have an angle of 109.5 degrees, near about. So see here, only three groups are there, right? CH3, this O, and this CX3. So these three groups are happy maintaining the angle 120 degree between them, But when one more OH group comes and attacks this carbon, the hybridization changes sp2 to sp3, means within angle of 109.5 degrees, the repulsion also increases between four groups. See, four groups, they should align themselves as 109.5 degrees, right? So that is actually a difficult process. So what happens, this O minus come back again, and one of these three should leave as leaving group. CH3, what happens, I'll say, this CX3 minus leaves as leaving group. Do you realize that CX3 minus, which if it acts as leaving group, it becomes an anion, right? So CH3 bond OH plus CX3 minus, right? This is actually anion. We very rarely we see anion as a living group everywhere. So this is stable because because of the fact that CX right, three halogen groups, a strong inductive effect. So the negative charge is stabilized due to inductive effect. So stabilized due to minus I effect. So what happens? This is formed. Now a proton transfer takes place actually. This I'll write like this. Okay, this comes and attacks over here. So it will result in the formation of bond O minus plus CHX3. This is the required haloform. Okay, this is I actually told you the carboxylate ion. If the base is taken as NaOH, then this will remain with CH3, C double bond O minus Na plus. If it is KOH, it will remain as O minus K plus. Simple. This precipitates down. This is the haloform. So similar to everything we have seen in alpha halogenation takes place, and finally OH attacks this carbon, and this can also be understood in a different mechanism. You take this one, right? What is this benzene ring? With it you take this one. This is acetophenone. So here also the same mechanism takes place. OH minus comes, abstract all these three hydrogens and form this one. Again, now you can understand clearly. Here there are no any alpha hydrogens to attack. So OH minus comes, attacks this, forms C O minus CX3. OH. Now again O minus comes, CX3 minus leaves, it forms PH, C double bond OH plus CX3 minus, proton transfer takes place right here. H plus transfer, here also H plus transfer takes place. It will become PH, C double bond O minus plus CHX3. Do you understand? So seeing these type of reactions, you understand one thing: only methyl ketones are able to give these kind of haloform reaction. Methyl ketones means what? You should have something, okay, to this one. This can be some, we will consider Y. Okay, it's not X, means X means it will consider as halogen. So Y can be R, H, or PH, or whatever. So any group can be there, but we as I told already in the previous video, we shall not generalize anything in organic chemistry. So basically I'll say some more compounds can also give alpha reactions. I'll say what are those. So as I said, some more compounds which has a particular structural arrangement can also undergo haloform reaction. For example, right over here, some other compounds that undergo haloform reaction. Example, take alcohols can also undergo this reaction. See, CH3, CHOH, HRRRPH. This actually oxidizes itself to form C double bond OH. So this is a methyl ketone which can undergo haloform. So similarly, you can take CH3, CH, HRPH. This will undergo in the presence of NaOH. Again, it converts itself to the alcohol. Substitution reaction. SN2 attack. So this can undergo haloform reaction. So these are one or two examples that can undergo haloform reaction. So the reagent used here is in the haloform reaction, we use NaOH in the presence of X2, right? So it can also be given as, NaOX plus NaX, or it can also be given as NaOX3 plus NaX. These finally generate this one, right? NaOH and X2 is also same thing. So in the examination they can give these also as reagents. So that's all about haloform reactions. And one more thing here, in the steps of alpha halogenation, you get three products, right? Sorry, two products, right? CH3, that is when one of the X is substituted here and another X substitutes here, right? CHX2, and finally it forms the CX3. So these compounds also can undergo haloform. This is the basic, right? This actually forms due to these two compounds. So this also can undergo haloform reaction. Okay, in the next video we'll see HVZ reaction, which is also a mechanism which also undergoes a mechanism through alpha carbon, and then proceed to aldol condensation. Thank you for watching.